All right. Good morning, everyone. Thank you all for coming. My name is Doug Hawkins. I am a JET engineer, as in just-in-time compiler engineer, at a company called Azul Systems. We make a VM designed at, let's say, demanding Java applications. We now support 2 terabytes of heap with pauses shorter than hotspot. And my job in particular is to deal with low latency messaging applications. These are sometimes people who measure performance in, believe it or not, microseconds. And of course, in trying to sell a VM targeted at performance concerns, we've seen and learned a lot about how to measure performance. We've seen a lot of problems, and that's kind of what this talk is about. It's about how your tools might be lying to you about performance. On some level, the goal for today is this quote from Niels Bohr, the physicist. He said, "An expert is a person who has made all the mistakes that can be made in a very narrow field." So our goal is to see some of the mistakes and to learn from them so that you'll be a little closer to being an expert. Honestly, performance is not a narrow field. It's pretty broad, but it'll at least give you some idea of what to look out for. Now, the biggest lie any programmer can tell themselves about performance is that they know something about performance. I've been doing performance exclusively for the last 3 years of my life, and each day I become more convinced that I don't know anything. That's just the nature of it. There's just so much that is involved that you do not understand. For instance, let's consider what a modern stack actually looks like. You're probably deploying a JVM, otherwise you wouldn't be here, on top of a containerized environment, probably on top of x86, and maybe you're using, I don't know, a solid-state drive. Well, let's consider what's involved there. A VM is a garbage collector and a compiler that are dynamically trying to guess what your application is doing and optimize for that. Then you're running that on top of a container, which is isolating you from the OS. The OS has a scheduler that's trying to guess the relative load of your box and schedule threads appropriately. Then your x86 chip, whether you know it or not, it's not actually CISC. It's a complex instruction set facade over a RISC core that changes every couple years in subtle ways, with multiple levels of caching. And then if you're using an SSD, your SSD has a garbage collector inside of it. Do you think you understand all of those? I am positive I do not understand all of those. It is difficult. And with a fairly simple program, I can actually show you what's going on in the VM and probably show you things you didn't necessarily know about. So Java performance is complicated. Here's the program I'm going to use. I'm just going to allocate a bunch of objects. That's it. I've got an inner loop allocating a chunk size of 1,000 objects, and I'm measuring its performance in a rather rudimentary fashion of just using system nanotime in an outer loop, and I print how long it takes to do each chunk of 1,000 objects. That's it. I'll run this program. It prints out a table of results. And we can see the program starts off on this MacBook Pro running at about 35,000 nanoseconds to allocate 10,000 objects, or 1,000 objects. And then if we keep going, it improves a bit to about 10,000, 12,000. And if we keep going still further, it improves to somewhat almost unbelievably good numbers. 40, 70 nanoseconds to allocate 1,000 objects. Okay. It's kind of interesting. And what you're seeing there, if you plot this on, in this case, a log scale, is you're actually seeing the just-in-time compilation workflow of the VM take effect. That first phase at around 40,000 nanoseconds, that's running in the interpreter, which is at least 10 times slower than the most optimized level of the JET. Could be 1,000 times slower. depending on how sophisticated the JIT is in handling the piece of code you're working with. After that, in Java 8, there's a first-tier JIT called C1. That's where those 10,000-ish numbers were coming from. We turn it on, and then if the method is hotter still, we'll kick in the second-tier JIT called C2, and that's where those 40 to 80 nanosecond numbers were coming from. And it really does have this sort of stepwise characteristic for an individual method, but across all the methods, it ends up being kind of a curve. And this is what happens as your application starts up. And you can see if you tried to write a benchmark for this, and you didn't run your benchmark very long, you'd be measuring performance in the interpreter. And the interpreter is 10, 100, 1,000 times slower than code in the second-tier JIT. That doesn't mean anything. If your code never makes it to the second-tier JIT, it cannot possibly be the thing that's making your application slow. Almost definitely. I know most applications I see, they do, let's say, around 8,000 compilations. About 2/3 of those are going to be in the first-tier JIT, and 1/3 is in the second-tier JIT. But the performance for most application comes down to like 1 to 50 compilations in the second-tier JIT. Those are the only ones that actually matter to the raw throughput of the application. And so if it's in the interpreter, could not possibly be important. So measuring the interpreter phase really means absolutely nothing. You have to measure the optimized phase, and you have to measure the optimized phase for methods that matter. But let's make the example slightly more complicated. Only slightly. I'm going to add a trap variable at the top, which is initially set to null. On the 400th iteration of the outer loop, I changed the trap variable to be non-null. I set it to a new object. And in the inner loop, when the trap variable is non-null, I print trap and I set it back to null. This is a boring example. Great, it's going to print trap once on the 401st iteration of the inner loop. Who the heck cares? That'll make the 401st run of the inner loop slower. Yes, it will. But there's more to it than that. We'll run it. Okay, roughly the same numbers to start with. Same sort of characteristic, dropping down to 10,000. We never actually get to like the 40 to 80 because there's a little more code there that's a little harder for the JIT to handle. So we settle in at around 600. And then when we hit our trap, there it is. Okay, the 400th iteration is a little slower, and the 401st is a little slower still at 100,000 nanoseconds. But that's the only one that did I/O, right? After that, there's no I/O. So why is the 402nd, and the 403rd, and the 404th slower too? The problem is we went backwards in the JIT workflow. What actually occurred was the compiler said, trap, it's always been null. I guess it always will be null. Despite the fact that it has evidence to the contrary, it's not very smart here. So it says, trap is never going to not be null. So I don't ever have to worry about printing out trap. So it's just flat out not prepared for that. And when that happens, we have to abandon the compiled code and go back to the interpreter. And that means we go back to running slow again. So if you graph this, you see a change from the 600, 800 nanoseconds that we were at, back all the way to the performance of the interpreter, not nearly for as long, and then it'll go again to C1, the first-tier JIT, and ultimately it will settle down into the second-tier JIT again, now running slower, prepared to print trap that will never actually need to be printed again. See how clever the VM is? But this is what it does. It's sitting here trying to guess, based on past behavior, what your application's going to do. And if you're not measuring the real-world behavior, you're not measuring anything that actually matters. If you pick one isolated piece of data It will optimize for that one isolated piece of data. Never mind that you have 1,000 other pieces of data when you're actually running your application. That's really not very helpful. Now, there are tools that try to help with these things, and the tools absolutely are good. You're starting to see that it is hard to measure the performance of a Java application. But tools can also lie. My apologies to all of you who are using JMeter for what is about to happen. Now, of course, I'm going to run JMeter, so I need something to benchmark. I used to be a web developer. I actually was a Java developer for a long time, and then came over to being a JVM developer. And this is the proof that I was a web developer. I can write a hello world for a web server with Jetty. So all it does is I have a single handler. It prints OK, or it sets the status to OK. It sets the content type to text HTML, encoding to UTF-8. And I didn't want to be wasteful here, so I pre-encode my HTML payload to UTF-8 in a static assignment, rather than doing that every single time. Don't want any of that allocation if I can avoid it. So we're going to run this server. Okay, my server is running. Check in Safari that my server is running. Yes. Hello world, excellent. And I have the world's most boring JMeter test. If you're wondering, should you run your load generation tool and your server on the same machine? The answer is no, but it does not matter for the purposes of this demo. I didn't want to bring a second laptop all the way from the US. So we're going to run this. It just makes an HTTP request to localhost, and I'm going to graph the results. That's it. All right, so it's running. It's doing about, it says 40,000 requests per minute. That's a little higher than I might expect. It'll probably drop down to about 25,000 on average. And so far, we've done about 12,000 samples if you look in the lower left-hand corner. Now, this server is going to experience an outage in a minute. The outage is called Control-C, but we're going to see what that does to our JMeter numbers. I'm going to let JMeter pick back up again. It tends to do this. It runs off to a high number, and then it backs down, and then it settles down to 25,000. OK, so server is going to experience an outage. There we go, outage. And JMeter claims we are doing 25,000 requests per minute. Do you believe that my server is doing 25,000 requests per minute right now? Top would seem to disagree since there's no server running. Let's try Safari. No. OK, that's only 3 samples. JMeter clearly knows better. But it says we're doing 17,000 requests per minute. Does that seem right? No. What is going on? Well, the problem is, again, in the lower left-hand corner, the number of samples. When my server is running, the number of samples moves really fast. When my server is not running, my number of sample moves in tiny little increments of 50. Oh, brilliant. So, when the server is running, we sample a lot, and that counts a lot. When the server's not running, we don't sample much, and that doesn't count much. What does this do to our average? It really doesn't work out all that well. Well, I mean, it works out well if your goal is to lie to yourself, which is what this talk is about. So the problem with what JMeter is doing is it's sending out samples continuously. And as long as it gets a response back, it sends out another one immediately. So when the server is up and responsive, it's running flat out. But when the server is not responsive, it sends out a request and it waits for the timeout. If you hit the timeout, you really should have done 1,000 more samples in that same time period before you hit that timeout. But that's not what it does. And of course, killing your server with Control-C is rather extreme, but all sorts of other things are little mini pauses, be it GC, thread scheduling, paging, all those sorts of things are mini pauses. And this results when you're using JMeter with these dark periods. Right after the server stops for being responsive, say when my GC happens, that period counts because I'm still sending out the full number of requests until I reach my threshold. But after that, until I reach the next timeout point, that's a dark period that doesn't really count. And it makes my numbers look really good. But of course, this is a sampling bias in statistical terms. It's a particularly pernicious form of sampling bias, one that my CTO, Gil Tene, decided to call coordinated omission, by which he means the system doing the load test is coordinating with the program being tested. It always counts generously for the good times and always counts also generously in the other respect for the bad times. Every time the application slows down, the measurement slows down, which is awesome for your average. So, the tip if you're using JMeter and you want good numbers is to maximize your dark period. You want to take full advantage of that timeout period. If you can get your GC to stop time to be a perfect multiple of the JMeter timeout period, that's how you get the best numbers, right? All right, so that's one fun example. Let's go back to the thing in the beginning. We said we need to find the hot methods, otherwise we're just wasting our time in terms of improving performance. Okay, well, how would we do that? Well, we use some sort of profiler. There are a couple options for profilers. You've got sampling profilers and you've got instrumentation-based profilers. Unfortunately, sampling profilers can lie. Let's take hprof. If I run hprof, it's convenient, it's there, you have it in your JDK, and I run it with an idle Jetty server, the one I used before. This is the output I'll get. It's telling me, on this machine, I'm spending 80% of my time in KQ array wrapper event 0. That's the I/O event system of BSD. And 20% of my time in server socket channel impl except 0. Well, if you're not aware, methods ending in 0 in the JDK are usually native methods. So all this is really telling me is I made a native call, and we don't know anything after that. It's not super helpful. But this is an idle system. Let's see what it says for a system that was under load. It's telling me I'm spending 80% of my time in KQ array wrapper event 0 and 20% of my time in server socket channel impl except 0. Wait, how is this helpful? I've learned nothing. I'm getting the same results if I look at the top ones. Yes. The problem with the sampling profilers, and unfortunately this applies to all profilers based on the JVM TI, i.e. the Java Virtual Machine Tools interface, is the samples include the threads that aren't doing anything. I know that my threads that aren't doing anything. I don't really care about them that much, unless I just have a lot of them, and then maybe I should dial it back. But this isn't terribly helpful. I actually have to get down to like line 23 in this report to find out, oh, what do you know? A server serving a request actually might be parsing HTTP headers. Brilliant. This is not a helpful report. And it's also not showing me time inside the VM itself. It's not showing me time spent in the JET or the GC, which might be important on certain systems. So they have a lot of limitations. There's a lot of errors of omission. But there's actually something even worse. Let's say I have this. I have function A on the bottom here. This is a visualization of it calling function B, and in turn calling function C. And time progressing to the right. And we could see just looking at this that we must be spending, I don't know, 30, 40% of our time in function C. Do do you think it's possible for a sampling profiler to never, ever, ever report function C in the profile? Well, with some probability, sure. No, with 100% probability. 100% probability this is possible. The problem is sampling doesn't happen everywhere when you're talking about a profiler based on the tools interface. It only happens at sample-eligible sites. These sites are called safe points. They're where garbage collection can happen too, but they're not everywhere. You probably think garbage collection can happen everywhere, but it actually can't. And so it's possible that you don't have one of these safe points in function C, so function C can never, ever, ever show up in a profile. Now, you'll probably get pretty good results. You'll probably see that, oh, I'm spending like 50% of my time in function B, and then it's up to you to understand, well, function B could really mean function C. But if you don't know about this problem, you could easily look in the wrong place. There is a solution to this. We could use instrumentation-based profiling. It's truthful. That is, we use a profiler that actually modifies the code. So it says, I'm going to put a little bit of code at the start of function A and B and C and record the start time. And I'm going to do the same thing at the end of C, B, and A and record the end time. And that will be accurate. Unfortunately, it's not accurate for the code that you're actually running, because you've now changed the very program itself. Adding that extra bit of instrumentation at the start of a method is going to be about 10 bytes for start and end. It takes 4 bytes to do a call. And the most important optimization that a VM does, or any compiler does, is inlining. And inlining in hotspot is driven by bytecode size. And the most important number is the second number in this table, the max inline size, which is only 35 bytes. Adding 10 bytes of overhead to every method call is a large amount of your inlining cutoff budget. That's a third. You have dramatically changed the inlining characteristics of your program. If it's in a hot loop, you'll probably fare a little bit better. There's this other cutoff that's actually bigger than the max. That's called the frequent inline size. It's 325 bytes. So 10 bytes out of 325 is less appreciable, but still, it's a problem. It doesn't do any good to get an accurate representation of the thing that you're not running. And sadly, even the JVM itself is lying to you. They're lies of omission. There are things that we don't tell you unless you know to ask. For instance, garbage collection. You've probably all looked at a GC log at some point, whether verbose GC or print GC details. Note that print GC details is actually more verbose than verbose GC. And you've seen stop time. But that stop time is how long the world was actually stopped, all Java threads. What it didn't tell you is how long it took to stop the world. The world doesn't just stop on a dime. The VM is a cooperative multi-threading system. Each thread has to behave itself. It's kind of like school children. You know, the teacher raises her hand and says, I would like to do a garbage collection. Please come to the circle. And 2 well-behaved school children gladly come over, and then the third one sort of wanders over later on. And then there's the fourth one, the one that the class all hates, who's still running around like an idiot, preventing us from doing what we want. And that's exactly the problem you can get into. A application thread can actually sit there and not come to stop. And if that happens, the GC doesn't happen yet. And that's not reported in the log by default. And Even my benchmark was a lie. I hope it was fishy that I was able to allocate 1,000 objects in 40 nanoseconds. I can actually allocate 10,000 objects in 40 nanoseconds too, and 100,000 as well. I'm not going to show you that, but I promise you I actually can do that. So it actually scales 0.1. That's awesome. No. The JIT is clever. The JIT does dead code elimination. It can actually say, you know what, you're creating an object inside this loop, but apparently you never actually use it. If you don't actually care about using it, I don't care about creating it. Okay, so we don't create the object, so it just gets eliminated. And then the JIT's like, well, okay, so now we got a loop with a no-op in it. Well, 0 no-ops, 1 no-ops, infinity no-ops, it's a no-op. Let's just do nothing. It's much easier to do nothing. And so that inner loop just goes away entirely. And so what my benchmark was actually measuring was how long does it take to call system nanotime and then turn around and call system nanotime again. And apparently that's somewhere around 40 to 80 nanoseconds. That's what I was measuring. It's really easy to write a benchmark that's wrong. Of course, there are solutions. I will show you some of them. Not all sampling profiles are liars, thank goodness. There are some that are better. HProf was an easy thing to pick on because HProf was never actually meant to be a production profiler. It was a demo of how to use the JVM tools interface, or maybe more honestly, how not to use the JVM tools interface. There is actually now a proposal to get rid of the thing in Java 9 so that people don't fall into the trap of using it. We do have better alternatives. Visual VM is a bit better. It's been with your VM since late Java 6, and I won't ask if any of you are still running Java 6 or, God forbid, Java 5. But you should have it. And if I ran it with an idle VM, or idle Jetty server, I'd get more useful results. It would actually still list a bunch of methods to me, but it'll tell me I'm actually not spending any CPU time on them, at least newer versions of Visual VM. When I ran this test last year, that wasn't true. So that's a little bit better. I can see that a server that's not doing anything is not doing anything. Revolutionary. But if I run it with a server under load, I start to see some things that are actually maybe a bit more useful. I'm walking on a poll operation on a queue, or a select operation, or accepting a connection. Those are where I'm spending my time, which, well, that makes sense because my actual response is very simple. So those things probably do dominate. But there is a better alternative still. Mission control. It actually comes from JRocket. As you now know, Oracle bought BEA, and they bought JRocket, and they bought Sun, and they bought Hotspot, and now they're merging the two together. And they're sort of trying to take the best of both worlds. And mission control is definitely a very nice tool. And if I use it on an idle server, and I've saved a profile from before, I can go and see the code and the hot methods, and hey, those are the hot methods for a server that's not doing anything. That looks about right. There aren't any. Okay, there's one. But that makes sense. And mysteriously on my laptop, it doesn't want to load another file without me restarting it, so I'm going to do that. And we'll look at what it looks like for a server that actually was under load. Note, I did actually use JMeter for all my load generation. I just don't trust anything it puts in its graph. As for terms of actually issuing requests, okay, I guess it's fine. All right, here are my hot methods for a server that's actually under load. And I'm actually getting something that starts to make a little bit of sense. My second entry is HTTP field get header. Yes, processing headers would be integral to processing an HTTP request. This is actually useful. And I don't have to do a diff against the other idle result to find the signal in my results. I just get a useful result. You'll also note that every single tool I've used has given me a different set of answers. HProf gave me one set, Visual VM gave me another, and Mission Control has given me yet another still. How do you decide which one is accurate? Well, I'll tell you this one's more accurate. The key thing about Mission Control is it has an interesting feature. Debug non-safe points if you run it on the latest VMs, like last 6-9 months. And what that does is it lets us profile anywhere. Method C won't be invisible. We will see only threads that are actually doing something. It does not have the same bias problems that exist with the other JVM TI-based tools. Unfortunately, as we're all developers who want to get paid but don't want to pay for things, Oracle wants us to pay for this. So, to use this, you have to use that set of flags at the top, unlock commercial features. This is your statement that you're either using this only in development. I don't know what perf test means in Oracle's licensing scheme, go check. Or you've paid Oracle some money to use this. Then you say flight recorder, that's the old name for Mission Control from its JRocket days. And then you have to use unlock diagnostic VM options, followed by debug non-safe points to get the sampling at any location. If you don't want to pay Oracle money, you do have some other options. There is the Google Lightweight Profiler. It was created by a guy named Jeremy Manson, who is the head of the JVM team at Google. Yes, Google has their own JVM team, as does Twitter, and let's see, I'm trying to think. Several companies have their own JVM teams. One of the financials does as well, but most of us cannot afford our own JVM teams. Google has that, and they've created this profiler. They don't really support it. I assume they use it in-house still in some capacity, but they don't really support it. It's a piece of code that you have to download and compile against the headers for the VM. And if you're like me, that's as far as you got, because when you actually tried to run it on your Mac, it didn't work. There's another tool that's a little easier to use. It's called the Honest Profiler by Richard Warburton. It actually has a GUI. It's not just a textual report. And it is, as it claims to be, honest. Both of these tools also can sample at non-safe points. And they do that by using a previously undocumented API in the VM that was always there, but we didn't know about because it was closed source. And then we were like, oh, that's cool, let's use that. And so now people are using it to get better information. The only real reason I mentioned the Google one is because Netflix has done some very cool work of pairing the lightweight Java profiler with a visualization called flame graphs, which is a very nice way to look at profile data. I have not actually invested the time to set that one up myself, but it's pretty cool, and they actually have gone a step further and made it where you can see all the way down into native methods too. So they're contributing changes back to OpenJDK. Again, you have to be running a very new VM to have these features. All right, I mentioned these safe points a few times. I thought I'd make it a little more concrete why you wouldn't have a safe point. The VM puts them all over the place. It just sprinkles them throughout your code. Everywhere there's a call, it'll put them, but it might get rid of calls by using inlining. Everywhere there's an allocation, there'll be a safe point. they're very frequently. However, if you're purely doing arithmetic operations, then you may have no safe point. So in this particular example, I'm creating a giant long array, 200,000 elements, and then I'm doing an n-squared operation over it, and there is no safe point in this because it's purely arithmetic, which means this n-squared loop over 200,000 elements will never show up in a sampling profiler. Not one of the JVM TI-based ones. Yeah, that's a little bit of a surprising result. Now, you can even ask the VM to be more truthful with you. You could say, could you please tell me about those other things? And it will. If you just ran your application with print GC details, then you'd see the first log line here in the middle of the screen. And it's saying, I'm doing a GC because there was an allocation failure. I adjusted the heap from this, I collected this much of the heap, and that took 0.008 seconds and 0.01 real seconds. Okay, cool. But if you use this print GC application stop time flag, then it'll print out the second line there. Total time for which application threads were stopped, 7.6 seconds. Yes, this was the same GC. Stopping threads took 7.59 seconds. And why? Because I was running the code I just showed you on the previous slide. An n-squared operation that at the first time was running in the interpreter, which is 1,000 times slower for that type of operation, and that took 7.5 seconds, in which a GC could not happen, and which you could not sample that that's where your time was going. And then there are a couple more flags we could use to get it to tell us about some other things that's hiding from us. It turns out it's not just garbage collection that stops the world. There are other things. They're small by comparison, but there are other things. Switching between different locking modes can stop the world. De-optimizing methods can stop the world. Not the flavor of de-optimization I showed you in the beginning, but there is another flavor that does. And if you use print safe point statistics and print safe point statistics count equals 1, you can get the VM to tell you about these things. Now, there's some debate among the VM people as to whether we should or shouldn't tell you about these things, because they are small by comparison to the actual GCs. But as the GCs get better, and these don't, they start to matter more and more. And there are tools I could use to have made my benchmark more reliable in the first place. I could have actually used a framework called JMeter, which was written by a guy named Alexei Shupalev, who is the performance tuning czar at Oracle. And it is a harness, just like JUnit is a harness, for measuring the performance of Java code. And you really write something that looks like a JUnit test. And it has this notion called a black hole to make sure that something like my object construction doesn't get optimized away. And it looks like that. Black hole consume my object. And it's designed so that the JIT cannot get rid of that. JMeter is very cool. We use it extensively at Azul. Oracle is using it to do performance measurement of the JDK as well. It is now part of the OpenJDK. But even with a tool like JMeter, which is taking a lot of the systemic measurement issues out of writing a benchmark, it is very easy to write a benchmark that has no bearing on reality. And it doesn't matter if you write a benchmark for something until you've proven that the piece of code is actually hot. So this is really the last thing I would go to. But there is one more lie. The second biggest lie behind I understand performance is my performance is a normal distribution. I'm afraid to tell you that if what you care about is, say, latency response of your application, it is not normal in the statistical words. Normal distributions are abnormal. If I actually fix my allocation example from the beginning to not do dead code elimination, and then I go plot a histogram, this is the chart that I get. I get several modes of execution. I get a very fast mode on the left. These are measured in tens of thousands of nanoseconds for, I don't remember how many thousands of items, but you can see most of it is skewed to the low side. Then there's this second little bump. I'm guessing that's allocation that happened right after a GC. And there's a little bit of extra setup work that has to be done. And okay, maybe both of those are normal, but taken as a whole, they're not. And then there are 3 measurements out there at the far right that are the actual GCs. They are 16 standard deviations from the mean. 16. That's okay, they're outliers, right? Well, okay. What's the difference? Why shouldn't I just say it's a normal distribution? Well, if I actually took all my measurements and I put them in order and I actually looked at the true 99th percentile, it wouldn't look so bad. The actual is 250,000 nanoseconds. The bell curve predicts 280,000. Okay, that doesn't seem so bad. But at 99.9, it predicts 340,000. The actual is 1.2 million. We're off by a factor of 4. 1.1 million. And much the same for 99.9. And if I actually go out to 99.999, there was actually a GC that took 2.5 million nanoseconds. This is not accurate. That's 32 standard deviations from the mean. This is not a normal distribution. This is what I don't recommend you tell your boss. That wasn't an outage. It was an outlier. You are technically correct. But he will probably say, yes, I hope it was an outlier for your sake. And at Azul, we've seen all these sorts of problems, and we've started to decide to create tools to help you see them yourself. And the first tool we created was something called JHiccup. It's to help you see these sort of other hidden effects that might be going on. Charlie Nutter, the guy behind JRuby, saw the tool when we made it available, and he said this: JHiccup, Azul System's free tool to show you why your JVM sucks compared to Zing. Yes, that is our reason for making the tool, and on some level, that's my reason for being here talking to you. But we also have a value in just educating people so that maybe they're more likely to buy our system. The way JHiccup works is it's just a Java agent that starts two extra threads. One measurement thread and one writer thread. And the measurement thread is really simple. It goes to sleep, and it sets itself to wake up a millisecond later and record what time it is. And it just does this over and over and over and over again. And believe it or not, it can do that with low overhead. And the reason this works is because any thread that's put itself to sleep is logically already at a safe point. It's already been stopped. And so it sees the full duration of a GC pause, even without using that extra VM flag. But it sees all sorts of other things too. It sees thread scheduling pressure because it didn't get its time to wake up. It sees memory pressure because it had to page stuff in. It sees all these sorts of things. And it has a mode to run not just your application, but another application doing absolutely nothing, also running JHiccup, so that you have a baseline to compare against. You'd be amazed how much a fresh Linux install with a VM running on top of it will still see 10 millisecond pauses. Just doing nothing. So JHiccup is nice, But to me, the nicer thing about JHiccup is what sits behind it. It has a histogram. But a histogram, of course, would grow size in. And when we have a very large spread of measurements, all the way from the low end up to our GCs at 32 standard deviations away, a linear-sized histogram might take up quite a bit of memory. And certainly, we can't just keep track of every single measurement when we have systems doing 5 million transactions a second. So instead, it uses an exponentially sized histogram. Since most of our measurements skew to the small side, it has size 1, maybe 1 nanosecond buckets on the low end, and then it moves up to size 2 buckets, and then size 4 and 8, and so on. And so you won't know exactly how long your GC pause was, or how long your other pauses were, but you will know I had 3 pauses in the range of, say, 520,000 to 640,000 nanoseconds. You'll have a bucket at that level of granularity, which is better than what most people are tracking. And then you can make pretty plots with it. You can take these histograms and feed it to a visualization tool, and you can get graphs like this, which show you your nines. The x-axis here is in terms of nines, the 90th percentile, the 99th percentile, the 99.9th percentile. And you can plot them and get a better idea what your actual curve looks like. I'll also note that the blue line here is Hotspot doing 2K Cassandra transactions, and the red line is Zing doing 20K Cassandra transactions. And so now you've seen a fair number of the problems and a fair number of the solutions. You're not an expert yet. There's still a lot more to this. But you're at least a lot more aware of the types of problems and the types of systemic problems your tools may have. Your vendors aren't necessarily going to tell you about them. It's not in their interest to do so. But they do exist. And I just want you to be a little more aware of that and double-check everything. All right? If you want some references on the topic, basically go read anything Alexei Shiplev has ever written. The guy is prolific. He works on the Java memory model. He works on JMH. He works on the JIT. I do not know how he finds the time. A guy named Fabian Lang did a much more detailed talk on profilers and their problems at the last couple Java 1s. Those are free to find online. You can find Jeremy Manson's blog where he describes some of the problems with profilers. And if you're more interested in some of the systemic measurement problems, you can go look at the blog of my CTO, Gil Tene. So thank you all very much for coming, and please feel free to ask any questions.